Okay, hello everyone. Welcome to our final lecture for the semester here in engineering physics. We're going to pick back up our discussion of thermodynamics. So the first thing that we want to mention is just a few more notes on, let me change that color. Okay. So a few more notes. On latent heat. And so one thing that we can talk about is this revisiting evaporation. Right? So we talked about evaporation already in terms of kinetic theory and molecules being able to escape from that surface of the liquid, even if it's just at room temperature and not anywhere near the boiling point. But we still need that latent heat to change from a liquid to a gas. So we still need the latent heat of vaporization to go from liquid to vapor, even at room temperature. Right, so that energy still has to come from somewhere. And so the process then of evaporation is this kind of, the heat is being pulled out of the water, the energy is being pulled out of the water in order to get some of it to go into that gaseous phase. So the the value of the heat of vaporization for water does change. So we can say, let's see, what do we want to write to you? So the value of heat of vaporization of water increases slightly with a decrease in temperature. So LV of H2O increases some with decrease in temperature. So in other words, it's going to take even more energy to have water go from a liquid to a vapor at lower temperatures. And so the example here is at 20 degrees C, for example, the latent heat of vaporization is going to be 2,450 kilojoules per kilogram. And if we looked at the same thing at 100 degrees C, at the boiling point of water, then that is going to be 2,260 kilojoules per kilogram. So you can see there's, an increase for that lower temperature. And so when we have water evaporating, we know that the remaining liquid cools down. And so now we know where that energy is going, right? So the energy to get those water molecules to leave the liquid phase and enter the vapor phase in the process of evaporation is coming from the water itself. And so its internal energy has to drop, and therefore its temperature has to drop, right? So this is, again, why evaporation can cool things down. And so let's see. We can also apply kinetic theory here. So we can make use of our kinetic theory to see why energy is needed to melt or vaporize a substance. We know that at the melting point, the latent heat of fusion does not act to increase the average kinetic energy or the temperature of the molecules in the solid, but is instead used to overcome the potential energy associated with the forces between the molecules. So at melting, the heat is used to overcome attractive forces between molecules. And of course, the same is going to go for vaporization, right? Okay. So there is some amount of work that you have to do against these attractive forces to break the molecules loose from their kind of relatively fixed positions. And when you have liquids, again, you still need to have some energy that you have to overcome to that is holding those molecules close together in order to get them to be a vapor. Okay. So now we're going to move on to the first law of thermodynamics. So up until now, we've discussed internal energy and heat, but we haven't talked about work, right? But work is often going to be involved in these thermodynamic processes. So we have work is often involved in thermodynamic processes. And so one way that you can kind of see that this has to be true is just by looking at the ideal gas law, right? So PV equals NKT or nRT. Either way that you want to look at it, it doesn't really matter. So we know that if we increase the temperature of a gas, that gas is either going to have to increase in volume or increase in pressure, or both, some combination of both. And if we say, well, let's assume that our pressure is constant, right? So when pressure is constant and we increase the temperature, then the volume is going to increase. But for the volume of gas to increase, it has to push any other gas or barriers or something out of its way in order to expand to that new volume. And so then it's exerting some force to do that. It's exerting a force over a distance. It's doing work, right? So we need to then take into account this work being done to truly analyze our systems here. And so work was another transfer of energy. So work is transfer of energy. And typically we're going to say that it's a transfer of energy to help distinguish them by some sort of mechanical means. And then we have heat, which is a transfer of energy. But this is specifically the transfer of energy due to temperature differences. So that's how we can keep these two things kind of separated in our minds. So we defined the internal energy of a system as the sum total of all the energy of the molecules within the system. So we would expect that the internal energy of a system would be increased if work was done on the system, or if heat was added to it, right? So internal energy increases if work done on the system or heat added. Similarly, the internal energy would be decreased if the heat flowed out of the system, or if work were done by the system on its surroundings, right? So say internal energy would decrease if work done by the system or heat flowed out. Okay, so since these are the two ways we can transfer energy into or out of our system, we can, just write down these kind of basic statements, which are hopefully very intuitive on exactly how the internal energy of our system would behave. So if we extend now our conservation of energy, we can then propose a very important law to thermodynamics, the first law of thermodynamics. And that is that the change in internal energy of a closed system will be equal to the energy added to the system by heat minus the work done by the system on the surroundings. So this is our first law of thermo. And I'm just going to write it in equation form because that is realistically how it is usually written down. And so it's kind of an interesting way for us to write this equation down, right? So we've got this Q minus W thing coming on here. And this basically arises because of thermodynamics was originally a science that was explored in order to develop some sort of system that could create useful work from heat, right? So we wanted to add heat and we wanted to get out useful work. So we were interested in the work done by the system. And then we wanted to know how much heat we had to put in the system to get that much work out. Okay, sorry, just getting a drink of water there for a moment. So this is heat added, and this is work done by system. Okay. All right, so this is our first law of thermodynamics. And again, you have to be very careful and consistent in following the sign conventions for this heat added and work done by the system. So since this is work done by the system, if work done is work done on the system, it will be a negative quantity, right? So then we get a plus sign in our equation. Whereas if we are considering the work done by the system, we treat it as positive, but then it goes into our equation with the minus sign already in front there. Similarly, if we add heat, then Q is positive. If heat leaves, then Q is negative. Okay, so let's see, what do we got here? So this is our first law of thermodynamics. It is one of the kind of great laws of physics. It's not quite as important as the second law, which unfortunately we won't have time to get to this semester, but it is one of the important laws of physics. And like I said, it kind of came about because of this interest in getting useful work out of engines. And really, it is kind of a broad statement of law of conservation of energy. Right, so it's just saying kind of whatever energy you started with is going to change by the amount where it's, the heat that you've added to the system and the work that you've gotten out of the system. And then that will help us out there. So when we talk about a closed system, particularly if it is an isolated system, then we can write things down in different ways. So it applies to either. But if we have some sort of isolated system, and what that means is that the work done by the system is equal to the heat added to the system, which is always going to be equal to 0, right? So then for an isolated system, our change in internal energy is going to be 0. So a given system at any moment is in some particular state, and we can say that it has a certain amount of internal energy. but the system doesn't have an amount of heat or work. So our system has certain E internal, but not W or Q, right? So those are not technically specifically associated with the system. Instead, when work is done on a system, say if we wanted to compress some gas, and you may have experienced this, right? So if you compress a gas, you have to, say if you're using a bicycle pump to pump up the tires of your bicycle, you have to push and apply force. You have to do work in order to get the gas to go into your tire, or to compress the gas. Or if we say add or remove heat, then we say that the state of the system changes. So if we do work on system / add remove heat, state of system changes. So the work and the heat are involved in the thermodynamic process to change the state of our system. So from some initial state to some other state, but they are not characteristic of the state itself. And so this is leading us into a definition here of what we would call state variables. Quantities that describe the state of the system. We call these state variables. And so these are things like the pressure, the volume, the temperature, the internal energy, the mass or the number of moles, M or N. All of those are state variables, but Q and W are not state variables. Okay. And since our internal energy is a state variable, that means it can only depend on the state of the system and not how we arrived at that state. So we can write down, so since E int is state variable, can only depend on the state. Not how it arrived at the state. And so if we looked at, say, some delta E internal, that's the change in energy from some state 1 to some state 2. That will be equal to this Q minus W. But the exact split between Q and W isn't really fixed by this equation. So our delta E int 1 E int 1 and our E int 2 are the internal energy of our system at those two states. Q and W are the heat added and the work done by the system in going from those states. But we can always write this out. And so since we can compute the internal energies based on temperature, we can always kind of calculate this side here. And then in combination with some of our other equations, so things like our specific heat equation, say, and the work done here, So this work has different amounts based on specific types of processes. So hopefully we can get to discussing those a bit. I think we should be able to get there. So we have this equation, and oftentimes we write our equation in differential form. So we would write this as this delta E int is equal to delta Q minus delta W. All right, so that is our differential form of this equation. So this is basically where we have some kind of infinitesimal change in energy when an infinitesimal amount of heat is added and an infinitesimal amount of work is done. So now let's look at an example of using the first law. So we have 2,500 joules of heat is added to a system, and 1,800 joules of work is done on the system. So we want to know, what is the change in internal energy? And so we have to just write down our first law here. So the change in internal energy is going to be the the heat added minus the work done by the system. And so since we have work being done on the system, that means that we have negative 1,800 joules there from our sign convention. So we have 2,500 joules minus 1,800 joules. And so if we plug in these numbers, then this is going to come to 4,300 joules. So that is going to be the change in internal energy that we have on of the system here. And again, this is because we have work being done on the system, so that is going to add energy to it. We also have heat being added to the system, so that also adds more energy to our system. And so in the end, we get exactly what we would expect, where we effectively add together the work done on the system and the heat added to the system. Okay. So now let's look into some applications of our first law of thermodynamics to actually calculate the work done. So calculating the work. And so here we're going to talk about different types of processes. And so basically in thermodynamics, what we like to do is simplify our processes by saying, let's hold one of our state variables constant and then see what that gives us as a result. So we're going to start with an isothermal process. And in an isothermal process, our delta T is going to be equal to 0. So our change in temperature in an isothermal process is 0. All right. So if our system is an ideal gas, so for ideal gas, then we know that we have an equation of state, right? So PV is equal to nRT. And so if we have a fixed amount of gas being kept at a constant temperature, so if we have fixed amount at constant temp, then what we know is that P times V is equal to a constant, right? So if T is constant and N is constant, R was our universal gas constant, so then everything on that side of our equation is a constant. And so in this case, we have basically as the pressure changes, as pressure increases, volume decreases, and as volume decreases, pressure increases, right? So you have this kind of relation between them. And so we've already seen plots of this before a couple of times now. So you have kind of these curves here like this, and then as you go to lower temperatures, they might look something more like this. So this would be higher T and lower T. And these lines are what we would call then isotherms. So our temperature everywhere along those lines, so we have pressure, volume, is going to be the same. All right, so what this means is if we assume that we have some gas that's enclosed in a container, but it might have, say, a movable piston, and that the gas is in contact with some sort of heat reservoir so that the temperature can be kept constant, right? So as we make kind of changes to the volume, the heat reservoir allows the temperature to not change significantly as we make these changes. So let's take a look at our system here. So you have some sort of container. We have a movable piston. And then we have an ideal gas in our container. This is a movable piston. All right, so we have some sort of heat reservoir outside of this so that our temperature stays the same. And we also assume that this process of compression or expansion is done in what we would call a quasi-statically. So basically just very, very slowly. So we can compress / expand very slowly. And so we call that quasi-statically. And so in this way, we can kind of assume that the system is always at equilibrium. So basically each kind of small change occurs, the system reaches a new equilibrium state, and then another small change occurs, and blah, blah, blah. All right, so we know that we're going to have some amount of heat being added to the system. So if we expand it, then we have to have heat added to the system. And we know that temperature needs to remain constant. So basically this is just saying that the gas will expand and do some amount of work W on the environment in order to help keep the temperature constant. So basically we can say that our change in internal energy, right, so we have delta E int is equal to our 3/2 nRT, 3/2 nR delta T, right? So if the amount of our gas is remaining constant, this is basically coming from the fact that we could say, we have 3/2 nRT final minus 3/2 nRT initial. That's exactly how we get there. And if n is constant and r is obviously a gas constant, and our 3/2 there is just a number, so then that gets us up to this statement here. And if our temperature is also staying the same, then we know that our change in internal energy is going to be 0. And so this tells us that our heat added or removed from the system has to be equal to the work done by or on the system, right? So this is for isothermal systems. Okay. So now we'll talk about this adiabatic process. And so for adiabatic processes, basically The amount of heat entering or leaving the system is 0. That is how we define an adiabatic process. And so obviously then from the first law, in an adiabatic process, we would say whatever our change in internal energy is, that's going to be equal to minus the work done by the system. And so we can use our other equations here. So we know, again, our delta E int, as long as our amount of gas is remaining the same, it's going to be 3/2 nr delta T. And we can use our PV equals nRT. And so technically from this, you can go into different types of processes, right? So you could say, well, maybe pressure is constant or volume is constant. We'll talk about those in just a minute. So in this case here, whatever, if you know the change in temperature, then you can compute the work being done in this adiabatic process. Okay. So then we have what we call isobaric processes and also volumetric, as your textbook says, but pretty much everyone else that I've ever talked to refers to those as isochoric processes. So isovolumetric is a little clearer as to what it means. It is, constant volume. So here you're basically saying that chain delta P is equal to 0. And here you're saying delta V is equal to 0. And so that will tell you kind of what's going on based on your your ideal gas law situation there, that equation. And so, isobaric process would be this one. So you'd go from some A to B that way. So this is isobaric. And if we had an isochoric process, that would be, say, something like this, right? So this is isochoric. Okay. So those are just conditions that you can apply. So if you're told a particular process is isobaric, then that's telling you that the pressure change is 0. And if you are told that a process is isochoric, then that's telling you that the volume change is 0. So that can be useful then in actually solving the problem. And so now we're going to talk about work done by volume changes. So as I've alluded to, when a system expands, it's going to have to do work on its surroundings to kind of push away that material of that surrounding in order to actually expand to that new volume. And so we often want to calculate the work done in a process where volume is changing. So again, let's say we have a kind of a contained gas in some cylinder that has a movable piston. Right, so we have some movable piston here, and we have our gas in here, and it's contained. So we have to, as always, kind of be careful as what exactly is our system. And so we're going to choose our system to be the gas, and so the container walls and the piston are parts of the environment. So we're looking for how much work is done by the gas. Okay. So, of course, the work being done here, if we compute some small amount, right? So let's say that this little piston here moves some distance dl. So there's going to be some force from the gas that we dot with this dl. And those are going to be in the exact same kind of direction, right? So the force is going to be of the gas is going to be pushing up if we're talking about expansion. And the displacement of the piston is also going to be upwards. And we also have seen that the pressure is force divided by area. And so the force is pressure times area, dl. And if we have area times dl, then that's going to be our change in volume, right? So that's just dv. So for a kind of small change here, we can compute then the amount of work being done. And so now all we have to do is go from our differential form of our equation to an integral. So we have the integral of the work, which is going to be the integral from some initial volume to some final volume of the pressure times dV, right? So this is a perfectly general, equation here. So we don't necessarily have any kind of specific conditions that we have applied to this just yet. This is just going to be the work done as a gas expands, right? So the pressure could depend on volume. It could not depend on volume. We could have situations where the pressure is constant, and so we get different expressions for different situations. So now if we revisit our idea here of an isothermal system, then in an isothermal system, our pressure is going to be equal to nRT over V, right? So that's just rearranging our ideal gas law. So we can plug that in to our work equation here. So we integrate from some VA to some VB. We have nRT, and then we have dV over V. And so these are just constants, and we get nRT out front, VA to VB, dV over V. And if you look up in integral tables, or you just remember from your calculus, the integral of 1 over a variable with respect to that variable is just equal to the natural log. And then using rules of logarithms, basically we can write that this is nRT times the natural log of the volume at B over the volume at A. So we just have the natural log of this kind of ratio of our volumes, and this is for isothermal ideal gas. Okay. When we have an isochoric process, right, in this case, we know that delta V is equal to 0, right? And so in an isochoric process, no work is done. So this means that W is equal to 0, because basically our dV up here would be 0, because the volume is not going to change, right? Or you'd be looking at it as you're integrating something from VA to VA, right? So you would get no work being done. So let's look now at an isobaric process. And so for an isobaric process, the pressure is a constant, right? So we have integral from VA to VB of pressure dV, but that pressure can be pulled out of our equation or out of the integral, because it is a constant. And so then we just have the pressure times VB minus VA. So that's a easy calculation to do. So this is basically P delta V. All right. And if we want for an ideal gas, we can kind of re-express our work done in this isobaric process. So then you have that the work is our pressure times this volume B minus volume A. And we can say, well, the pressure, if we say, well, let's take the pressure specifically at point B, right? So then we know that pressure at B is equal to nRT over V at B. So we can plug that in. And what we get is that the work is nRT 1 minus VA over VB. And so those are our different ways that we can compute the work being done in different processes. Okay. All right. So let's see. Let's take a look at an example. And so this will be kind of where we're going to end for the semester, so we won't get into things like molar specific heat or the equipartition of energy or adiabatic expansion or conduction and convection and radiation and all those fun things at the end of this chapter. But like I said, that is our reality right now. So in this example here, we say let's have an ideal gas being compressed slowly at constant pressure of 2 atmosphere from 10 liters to 2 liters. So we have ideal gas slowly compressed at constant pressure from 10 liters to 2 liters. And there's a diagram that shows us in the textbook, figure 9.13. So this process is path B to D in that diagram. So let's draw out the diagram that they show there. So we have our 10 liters over here. We have our 2 liters over here. So here's our 2 and our 10. This is our volume. Then we have our pressure. And so we have this kind of process here. Let's erase this a little bit. So this is the point that we label B over here, and we label this point over here D. Okay. We then have heat being added. So in the process of compression, some heat is going to flow out of the gas, and the temperature is going to drop. Then we have heat is added to the gas, holding the volume constant, and the pressure and temperature are allowed to rise. So that is going to be along some line here. Okay. So then our volume and pressure and temperature are allowed to rise until the temperature reaches its original value. So this is point A here, and we have that T at A is equal to T at B. And so these would be connected by one of these isotherms here. So this is an isotherm. All right. We want to calculate the total work done by the gas in the process of going from B to D to A, and the total heat flow into the gas. Okay. So we have to then say, all right, well, let's look at this compression from B to D. We can calculate the work as this P delta V, right? So we just have a change in volume at a constant pressure. So we call this some PB down here. We'll call this PA up here. Okay, and we know that this pressure down here, this PB, is our 2 atmospheres, 2.0 atmospheres. And we need to convert that, but let's see, we have 2 atmospheres, and our change in volume is from 10 liters to 2 liters, so other way around, sorry. 2.0 liters minus 10.0 liters. And so if we convert all of these numbers here, the 2 atmospheres of pressure, we multiply that by about 1.01 times 10 to the 5, so we get 2.02 times 10 to the 5 newtons per meter squared. And then we convert our liters into cubic meters, and that's going to be 2.0 times 10 to the minus 3 meters cubed minus 10.0 times 10 to the minus 3 meters cubed, and multiply that out. And here we get minus 1.6 times 10 to the 3 joules. So that gives us the work done by the gas as a negative sign. So that means that we actually did work on the gas, right? And then we want the isovolumetric. We do no work, right? So from D to A, our delta V is equal to 0, so work equals 0. So the total work is this minus 1.6 times 10 to the 3 joules. Okay. Since the temperature, so this is part B, we want the total heat flow, right? Part B, total heat flow. So this tells us, since TA is equal to TB, if we go back and write the internal energy then at A, it's going to be equal to our 3/2 nR TA, and our internal energy at B, we could say, is 3/2 nR TB. And so in this situation, when we look at that delta of our internal energy, that's just going to be equal to 0, right? Because TA is equal to TB. When you subtract these two things, the final minus the initial, you get 0. And so this is also got to be equal by our first law to this Q minus W. And so in other words, we have that Q is equal to W. And so in this case, our Q is equal to W is equal to minus 1.6 times 10 to the 3 joules. So heat is lost and work is done on the system in this particular process. All right, so that is that example. And that is, I think, where we will end for this semester. So I might end up posting next week some sort of additional exam review. So this would be kind of like a replacement for our quote-unquote Friday session, which we haven't really been using since we moved things online. And so I might next week record a final review, so to kind of prepare you guys, hopefully, for the final exam. That final exam will be very similar to the last exam that we took in format, so it'll be kind of just sort of calculation problems where I'm asking you kind of conceptual things in the beginning parts of those problems, and then having you do some calculation. The equations will be given to you in the problem, so you'll have a question that says, which equation are you going to use, and that'll be part of the credit for that problem. So anyways, I will send out information via email about the final, and like I said, I will try to post some sort of just review to kind of very, very quickly and briefly talk about some of the things that we've gone over this semester. So until then, we will end things here.